let's look at conservation of energy, and this is in Chapter 10 of your textbook, Glencoe Physics. So with conservation of energy, our total energy is equal to the kinetic energy plus the potential energy. So to use variables, our E total is equal to kinetic plus potential energy. And to remind you that kinetic energy is 1/2 the mass times the velocity squared, and potential energy is represented by U, and that's the mass times the acceleration due to gravity times the height. So we're looking at gravitational potential energy. So here's our example problem. It says determine the potential, kinetic, and total energy of a 20-kilogram rock at the top of a 100-meter cliff. So there's the question at the bottom. So let's first have one column, that's kinetic energy, a second column, that's potential energy, and our third column will be total energy. So the rock is sitting there without any motion, so V is equal to 0. So remember, kinetic energy is 1/2 mass times velocity squared. Since velocity is 0, our kinetic energy is 0. Now, potential energy, remember, is your mass times gravity times height. So our mass was 20 kilograms, that's the mass of the rock. We know what gravity is, 9.8, and our height is 100 meters. So we can calculate potential energy as 20 kilograms times 9.8 meters per second squared. Let me move this over a little bit. Times the height is 100 meters. So if we use our calculators, our potential energy, usually a big number, this equals 19600, or 19,600. You might remember these are joules. So up at the top, it's all potential energy and no kinetic energy because the rock's not moving. So our total energy, I'll do it in red, is 19,600 joules. And that's going to stay consistent through the whole problem, this total energy. So now the rock's falling halfway. So we're 50 meters down the cliff. So again, we're going to look at potential, kinetic, potential, and total energy. Total energy has to equal 19,600 and joules. No and. Now, the easiest way to do this is to think about total energy is equal to kinetic plus potential. Potential energy is based on height, so that's easy to calculate. So if we can figure out our potential energy and subtract it from the total energy, we can find kinetic energy. There's also other ways you can figure out the velocity of this rock, but I believe this is the fastest. So finding U, I'm going to take my mass, it's 20 kilograms, my G is 9.8 meters per second squared, and my height is 50. And you do the math, or you could just count your total energy, cut it in half, and you get 9,800 joules. Your kinetic energy is 9,800 joules. So we're looking at the 50 feet that it has in relation to 0. Okay, so that's the potential energy it still has. And since it's falling, that's the kinetic energy. Those are little ripples in the air. Now, let's look at its energy when it's at the bottom. So now it's still moving, so it does have velocity, but it's not above the Earth. So we know potential energy this time is 0. Your total energy is 19,600 joules. So your kinetic energy is 19,600 joules. Remember, your kinetic energy plus your potential energy always has to be a constant number. Now let's figure out the velocity of this rock right before it hits using kinetic energy. Find the velocity of the rock right before it hits. So, we know that kinetic energy is 19,600 joules. We know the mass of the rock is 20 kilograms, and we're trying to find velocity. There are other ways of doing this. You could use your kinematics, but I just want to show you a different way. Remember, kinetic energy is 1/2 mv squared. We're solving for v. So we have 2 times k divided by m gives you v. So I multiplied both sides by 2 and then divided by m, and since it equaled v squared, I took the square root. So let's work this out. V is equal to the square root of 2 times 19,600 joules divided by 20 kilograms. Your velocity is be sure to square root your numbers. I have 44.3 when I round to 3 sig figs meters per second is my final velocity. Now your units, if you remember, a joule is a kilogram meters squared over seconds squared. The kilograms are going to cancel, and then you're taking the square root of meters squared seconds squared. So this is a very brief introduction to potential and kinetic energy and how it's conserved when falling. You'll be using this in your egg drop calculations. The end.